Okay, I've told you that the Muscovite mica is a kind of template. Why is it a kind of template? If you cleave this sheet silicate at this position here where the potassium counterions are, you end up with a single crystal that has a fairly flat surface area, very bright surface area with some grooves along it, along one of the high symmetry axes, and you have strong uniaxial electrical fields almost perpendicular to these grooves. And what happens is that the uniaxial electrical fields then orient the molecule along the most polarizable axis of the molecule, which happens to be the long molecule axis. And then the molecule arranges in a way that it optimizes the CH-pi interactions in an organic molecule. Okay, this is the supermolecular order that's going then, and then it's growing along the grooves. So this would be the long fiber axis then, which is then almost perpendicular to the uniaxial field. So that was the point where the physicists came to us, we need new materials. If you look at this packing here, which is pretty important for the material property, because only in this way we have this nice conjugation of the pi systems, so this is very important for the properties. The only thing that you can think of is these power positions here, so these end positions here, because they do not interfere with the packing. If I would introduce any kind of group here or there, the packing would be gone, and the properties would be gone. We would have nice molecular properties, but we won't have material properties. So I don't know if so many organic chemists are here, probably not. So I can tell you these kind of molecules, stones, are very good soluble compared to these materials. Okay, this is just a solid. So solids is not the thing that organic chemists like to work with. We always like to work with molecules that are soluble. So that's why we cut off usually several of the aromatic systems there and make smaller oligomers from this. So here's a whole bunch of different molecules that we've made. So we have not only these oligophenylines, where you have only these benzene rings here as an oligomer, but we also introduced alkynes, we introduced thiophenes, pyridines, carbazoles, pyrimidines, all these kind of heteroaromatic molecules that then change the optical properties. And you can see here the molecular properties. The colors are not that good. Most of them emit blue light, but you can also have something that looks like text marking, so bright yellow emission, and so you can change the properties more or less at will. Before I forget, the picture of the people here, these are the PhD students that actually do the work. I'm only telling the story. So, yeah, so introducing then functional groups, as here, these methoxy groups, or here, these cyano groups, or the chlorine groups, actually have a good influence on the material properties, so they really aggregate in a fine way. Remember that the picture that I showed you before had 6 of these aromatic rings. Now we have only 4. If you would use the non-substituted tetraphenylene, it would not form any aggregates at all. But with the functional groups on, we get these nicely nanofibers again, blue emission, this is nice, and we can also control the morphology of these materials. So either we have cross-sections that are half round, or like a rectangle, or like a triangle, although I have to admit I have no clue why this is. So it's reproducible, really nicely reproducible, but I cannot really tell you why this compound likes to make this prism-like arrangement, whereas this compound likes to make the quarter-like arrangement. But it is like this, and as I said, we can transform them to different surfaces, then rearrange them and make optical devices, and I will show you in a minute. By introducing functional groups, I can also enter new properties that cannot be found in the symmetric molecules. So one of them would be the nonlinear optical properties, and we have shown this by introducing different functional groups here. So thereby we disturb the centrosymmetry of the molecule, and then we did a second harmonic generation test. So what we do is we use a high energy infrared laser and look whether we can get an emission of the material that has then the frequency doubled signal. So if we use an laser with 830 nanometers wavelengths, what we get is an emission at 415 nanometers. And as you can see here, 790 nanometers, we get 395. 770 nanometers, we have 385 nanometers emission. In fact, these materials are very effective. I'm very glad that we now have this green laser pointer here, because in this green laser pointer is not a green laser diode. This would be probably much, much too expensive, but there's a red laser diode in it. And then there's a material then that doubles the frequency, and therefore we see green light here. The material that is in this laser pointer is this KDP, which is kind of the standard material for the second harmonic generation. And as you can see, the absolute number is about 0.8 for the C square. And our materials are 3 times better sometimes, like this material here. Of course, I have to admit, I can't crystallize it in this way like I could do it with KDP. But on this nanometer or micrometer scale, our things are better than this inorganic material. Okay, you can also introduce then the other heterocycles as I've shown you. You sometimes get different morphologies of the nano aggregates that you get. So this looks more like spaghetti, short spaghetti. But then you have also, again, linear things, but more than one cross direction. And then you have also here some more irregular spectrum, depending on which compound is used, but you can also see that the color changes by the conjugation length of the molecule. Interestingly, it also accepts very large substituents. We were very surprised about this, and also chiral. So we again get nice nanofibers, nice mutually aligned with a half-round cross-section. You can see it more or less here. And we have really narrow distribution of the fiber orientation and the polarization of the emitted light of these compounds. So here's again another compound, the carbazole, again, nice mutually aligned nanofibers, but the point why I show you this compound is that these heterocyclic compounds often show a much better solubility than the compounds that are only carbon-based. And much better solubility then also gives us a nice opportunity to also use different deposition techniques. You've seen the apparatus that we use for gas phase separation, a pretty expensive technique for making large things, okay? So it would be much better if we could make it from solution techniques, and therefore we used the deposition from solution, also in an inorganic template. It's a anodic aluminum template that we use. Here's an SEM picture of this template. And here are some of the fibers that we got from this deposition in this template. Here are also SEM images of these fibers. So, of course, the dimensions of the fibers are now controlled by the template, but still we get these fibrous aggregates, which we can then rearrange. Here you can see a single one that we have actually prepared then to look at it with AFM. And the optical properties are almost the same as the one that we get from gas phase. The gas phase is a little bit better because the crystallinity is higher than this one, but still it's much, much cheaper, and you get a reasonably good performance. Here's another one. The template technique has another, so the solution phase deposition has another advantage, and this is that we can also now use smaller oligomers which we can't deposit from the gas phase because they're just too volatile. They would not sublime on the surface. We would just evaporate them again. And so we can also use them, probably you can see it here best, to make these fiber-like structures which can then be rearranged and used for other purposes. So what kind of purposes can we do? We can make light-emitting devices, like, for instance, not an organic light-emitting diode, but an organic light-emitting field effect transistor. So what we do is we prepare a thin film of these molecules. This one is actually this one, and this one is here. I think you can hardly see it because I can hardly see it. So the emission of this one is green, as shown here. And the device actually provides green light in this AC-driven OLEFET configuration. And this one here, due to the larger pi-conjugated system, then emits an orange light in this device. We can also use these fibers then for organic phototransistors, so as light sensors, for instance. So we deposit the fibers on this transistor, and then if we shine light on it, we get the electric signal, and we can measure. So we have a micro sensor, so to say, for light. And of course, we can also produce energy. So far we have put in light and got light out. We have put in electricity and we got light out. So now we can put in light and get electricity out, but therefore we again have to change the structure. So we made these compounds here, which are called squarenes. These are Twitter ionic pi-conjugated oligomers, very interesting compounds because they are very stable. And together with this acceptor material, this, the important part is this fullerene looking like a football molecule. Actually, this is the C60 molecules only from carbon, which really looks like an old football, so to say. The new footballs have a different scheme. But the old ones were like this with this form. And you can make solar cells from this. Actually, these are bulk heterojunction cells where we have an active layer of the donor-acceptor blend in a more or less irregular manner, not layer by layer. And we can make then photovoltaics from this. Okay. So what we would also like to do, and I think this is a big important advantage of organic chemistry, is that we combine this with other purposes, not only making the solar cell. As we've heard already, there are very good solar cells from inorganic materials, very stable, long-lasting, everything. The only thing is that they are very heavy, this size, and they are, of course, not transparent. Organic photovoltaics might be semi-transparent, so we would also only need a certain portion of the solar spectrum, and the other light would just go through. So you might combine this, for instance, with a photobioreactor, which is nothing else than an aquarium where algae are growing in. And you would cover the one side with a semi-transparent photovoltaic cell, so the green light would go in, the algae could grow, but the rest of the light could be used for making electricity. We've also heard about the problem of storing energy, also from solar cells. This would be perfect because the bioreactor needs some kind of electricity, and it needs more electricity the more the algae grow. They grow the more light shines. So the more light shines, the more the photovoltaics will deliver electricity. So we have a synchronous making of electricity and use of electricity. So that would be perfect. We don't have the problem of storing it. We would just need it, or produce it where we need it. Right? Therefore, what we have to do is we have to adjust the absorption spectra of our material in that way that the absorption of the chlorophyll molecules is not affected. So we have to make molecules that affect them. This is very difficult to achieve with inorganic materials, much easier with organic materials. And then again, we have only a very thin layer of our material. We don't have something that is this big like in inorganic materials, so that might be a very nice opportunity. Also, you could use this thing, or think of this use of this technique for greenhouses, where you actually, what you do is you shade, not to get too much sunlight and too much heat into the thing. So use the shade also to produce energy. That would be really nice. Okay, with this, I'm at the end. I would like to thank a lot of people. You've seen the pictures already on the perfect. So these were my past and present co-workers that are working on the synthesis of the one, but not only on the synthesis, they also visit our physicist friends and then actually make the solar cells or the phototransistors or the olefets themselves in the group, especially of Horst Günther Urban in Sonderburg and his colleague Frank Balzer. Now we've also made a connection with Manuela Schick. She was also a former co-worker of mine. She's now in Oldenburg working on the photovoltaics. And Rainer Koch and Katharina Alshamri also brought us into the game. Okay, with this, I would like to thank you very much for your kind attention. And once again, thank you very much for making me part of this meeting. Of course, we have a problem. We also have a problem concerning the intensity of the sunlight. For Europeans, it's not too bad to have a good performance with not too much intensity. That's what our squarines advantages for special techniques. For instance, if you would like to cover your whole facade with different shades of colors, which produce energy, this is organic chemistry. You need them. You could print it. I've seen it that they now print it in Dresden in a meter. So this is really then also getting very cheap and really nice attitude.
Okay, thank you. Thank you, Professor Chemmis, for your kind introduction. And also I'd like to thank the organizers, especially Professor Pal and Professor Parthasarathi Mukherjee for the kind invitation. So I'm very thankful for the previous speaker for kindly, in fact, he has given, nicely set up the introduction for my talk, because I'm also an organic chemist and a supramolecular chemist working with pi-conjugated systems. So my group is Supramolecular Chemistry Laboratory. We work at the interfaces of organic synthesis and self-assembly, and thereby trying to make functional materials. Okay. As the previous speaker already mentioned, we again work on supramolecular chemistry, pi-conjugated systems, so that we can get electronic and optical functionality out of it. Okay. So the question is, so already nice introduction was there. Why should these supramolecular chemists work on pi-conjugated system? So the one of the major thing is that when you look into this organic electronic devices, the efficiency of these devices not only depends on the molecular structure, but also depends on the supramolecular organization. And rightly pointed out by the previous speaker, again, it's not only at the nanoscale, you need a nice organization at all length scales. So you need to go to have a higher domains. So that way it is very important, and right now supramolecular chemists doesn't have it, clear strategy to control this organization of this molecule in a bigger scale. If you like a bulk device, it's impossible to control the organization at all length scales. So we do have some control at nanoscale, but it's important to get a control at the higher domain scales. So that is one of the challenges, and that is why supramolecular chemists work on pi-conjugated systems. And so you already see, like most of the organic electronic devices, they have pi-conjugated polymers. But one of the problems in working with this pi-conjugated polymers is often it's very difficult to get, completely pure. You will also always have some structural defects associated with it. So one alternative it is to work with pi-conjugated oligomers, which is monodisperse, and you can make it synthetically completely pure, and then you can control their organization, get a higher efficiency out of these devices. So these are two approaches available, and again the previous speaker mentioned he works on pi-conjugated oligomers. The advantage is we can get it 100% pure, and it is completely monodispersed compared to the polymeric system. Okay, so this is one motivation behind supramolecular chemists to work with pi-conjugated system. And a completely different objective is, sometime back, supramolecular chemists have asked a question: can we make pi-conjugated nanostructures of these molecules? Okay, so it is just like a carbon nanotube or inorganic nanowires, and can we make them conducting? So this was just a curiosity people have asked. So you know that inorganic structures and carbon nanotubes have been tried. Can we make the corresponding analogs of organic structures? So this was a couple of motivations for us to work on this pi-conjugated molecules. Okay. So these are our toolbox. You know that this is p-type. If you talk about organic electronics, you should have a p-type molecule which is donors, and we should have n-type molecules which is acceptors. Okay. So well-known p-type molecules are oligophenylmyelins, and then we will have hexabenzochronin, whereas n-type is perylene pisamides and fullerenes and coronins and so on. Okay. So a lot of knowledge has been accumulated in supramolecular chemistry. So it's no longer a challenge to make a 1D nanofiber of such pi-conjugated system. For example, this is a famous example from Takuza Eda group. This is a p-type material which is a hexabenzochronin structure. As soon as you can make, you see that if you functionalize with an amphiphilic structure, that means it has a polar group as well as a non-polar group, you can see that they form nice one-dimensional nanotubes. So first they form a bilayers, and then they form a sheet, and then roll to form a nanotube. So these are conducting, and or let us take n-type materials. This is a well-known example from Frank Buchner's group in Germany. So he used a perylene pisamide, and you see that you can attach a hydrogen bonding loop to it, and you can make 1D fibers out of it. So this is no longer a challenge. You can make 1D nanostructures of pi conjugated molecules. You just apply some supramolecular chemistry design principles, and they will organize into 1D structures. Okay. So the most important question is, are they really conducting? Okay. So when most of these fibers, when they try to transfer onto substrate, or this is different from the transistors, general organic filter transistors. I'm talking about a single nanofiber transistor made up of organic nanofiber. Is it possible to make such devices? And so most of these fibers, when transferred onto devices, the performance was very bad. They are very bad conductors, and most of them are insulators. So this was quite puzzling. It could be due to many issues because of the low mobility along the stacking direction of these molecules, or it is due to some insulating problems, because there is no real fabrication techniques available to make organic FETs. I mean, nanofiber FETs especially. So what people do is just drop cast these fibers on a between electrodes and look for single fiber, and then try to measure conductivity over it. Okay, so that was one of the challenges. So when we started few years back, so one challenge we tried to address was to can we make a conducting nanofiber transistor, again a single fiber transistor. So one of the ways people try to improve their conductivity is to dope it. I mean, just like a P-type, if it is an organic donor molecule, you can always oxidize it, thereby you can introduce charge carriers, or if it is N-type molecule, you can always reduce it and thereby introducing charge carriers. This was doping is people have tried. So, but one of the issues with this doping is it can often destroy the self-assembled nanostructures. They are very soft, so by doping you can easily destroy them. And always it is difficult to get uniform doping in these devices. So, in this respect, there is another class of molecule which is called charge transfer systems, which is nothing but a mixed of multichromophoric system of donor and acceptor molecules, which are organized cofacially. Okay, so face to face, you can see that this is called a mixed stack charge transfer system, and this is an orthogonal charge transfer system. And this is a well-studied TTFT CNQ system, which is known to have conducting. So the question we asked was, can we make a supramolecular analog of it? Can we make a conducting organic fiber which has a molecular organization of donor and acceptor molecule, which is cofacial to it? So that was the interest. So the challenge is how to make such a nanofiber, which is having alternating arrangement of donor and acceptor. So we came. So that was one of the challenges. So we started working on a variety of donor acceptor molecules, especially with the mixed stack organization, where donor and acceptors are alternatively organized. Okay, so we not only use them for conducting nanostructures, but we also use for a variety of other applications, which I'm not going to talk about today. And also the advantage of this system is they have very high association constant. This donor and acceptor molecule, that is a nice supramolecular motif. You can make it reversible by just oxidizing the donor, or by reducing the acceptor. You can nicely break this assembly to individual donor and acceptor molecule. So these have very high association constant, and we can make them highly reversible as well. So this can also be used as a nice supramolecular motif. So so let us see how we make this kind of donor acceptor nanostructure. So we have come up with something very simple non-covalent amphiphilic approach. This is nothing but if you take a donor and acceptor in such a way that if you synthesize in such a way, when it forms a face-to-face this charge transfer complex, if it is structurally resembles a surfactant, and you put it into any solvent, it should immediately self-assemble, especially in a polar solvent. And you should get 1D nanostructures with a perfectly alternating donor acceptor arrangement. That was a simple idea. So we came up with a variety of donor and acceptors. We have synthesized especially choronin methylviolacin, oligophenylmylene, perylene piscimide. And so as soon as it forms a donor acceptor system, you can see that structurally it will have a surfactant design, okay? And as soon as then you put it into a polar solvent, they form nice 1D nanofibers, nanostructures, so it's a completely solution state technique. And most importantly, we have collaborated with physics group and like Professor Kulkarni from our own institute. So we have made single fiber nanotransistor, and indeed they were promising. They showed impressive mobility properties. So this was one of the approach we had to address this electronic functionality. And later, now probably a couple of years back, there was a sensational paper from Northwestern group that this kind of mixed charge transfer crystals are shown to have room temperature organic ferroelectricity. Okay, so what we should have is a stronger donor acceptor pair, which is having a higher ionicity. That means the extent of charge transfer should be high. In these two systems, it is much lower, but we have now started working on tetrathiophulvalene and NDI system, where the extent of charge transfer is like around 0.75 if you calculate the parameter, which is good enough for an organic ferroelectric. So we are trying to make organic ferroelectric nanostructures based on this kind of design. Okay, so these are some of the activities on electronic functionality, but today I will be more focusing on our activity towards optical functionality. Okay, so as pico-educated system, not only they have electronic functionality, they have highly luminescent, and probably you may know already organic based OLEDs are already in the market, especially Panasonic came up with a big TV recently with organic molecules. So during this talk, I'll be talking, in the first part, I'll be talking about can we use an hybrid approach? That means inorganic approach to control this dye organization, and also later can we get a tunable emission for using light harvesting. And we call it as soft hybrids because unlike many conventional hybrids, our hybrids are solution processable. So so that's the reason we call it as soft hybrids. So there are multichromophoric organic assemblies are well known, and especially when it has a donor and acceptor inside it, you can have a nice energy transfer from the donor to the acceptor, and such systems are called light harvesting system. Okay, and so this is initially people are interested in such systems mainly to understand the basic photophysical process involved in artificial photosynthesis. So people came up with dendrimers, designs such that the donors are in the antenna, act as antenna, they are at the periphery, and the acceptor molecules are at the core. And there's a nice energy transfer from the periphery to the core, and they're nice, they're a nice model system to understand this energy transfer process and light harvesting process. But later people immediately realized that this is also, it's a nice method to make luminescent materials with tunable emission. So if you want to get a particular emission out of it, you use that acceptor and you can extract the emission from that particular acceptor. So this is also luminescent materials. That's another interest, and people came up with multi-chromophoric system like organogels and all sort of things to make tunable emissive materials. This is not inorganic assemblies. But one of the problems with these pure organic assemblies, not on all molecules, but certain molecules, once it comes to this aggregated state, they often, especially when they have a cofacial organization which is called H aggregate, they often quench their luminescence. So this was one of the drawback of pure organic systems when it comes to their quantum efficiency. So they are weakly fluorescent. So with this objective, recently many groups have started coming up with a hybrid approach where you use an inorganic template for the spatial organization of these organic molecules. Okay, so that way you reduce the intermolecular interactions, at the same time they become more fluorescent. Okay, so these are a couple of typical classical systems known in literature during the last, let's say, 3-4 years, like metal organic frameworks, where their ligands are either donor or acceptor molecules, or periodic mesoporous silica, where their wall is a donor molecules and the acceptor molecules can be incorporated into their pores, or zeolites, where the walls are made from, in zeolites, both donor and acceptor molecules are incorporated into their nanochannels. And they all are showing efficient energy transfer, and they are nice light harvesting hybrids. But one of the issues with these systems is that there's poor solution processability. So one of the beauty of the organic systems where they are nice solution processable, so you can make a spin coating and make a large area display devices. But when it comes to these kind of hybrids, they are less processable. It's very difficult to process them, any of them. There were some attempts to improve that, especially in MOF. Recently, nanoscale MOFs are coming up where we can make dispersions out of it. And in PMOs, what they have tried is to make a film of the monomers and do a pre-synthetic polymerization on the surfaces. And also in zeolite, people have tried to make a polymer zeolite composites. And there are attempts to improve the processability in this case in the hybrids. But it lacks a modularity. It is very difficult to tune the processability of this material. So with this approach, we thought, can we come up with something called soft hybrids, where we can introduce both solution processability as well as the finer hybrid properties of this system. Okay, so what we need is a real supramolecular approach, and for that we need to have a inorganic component which is soluble in particular solvent, so that organic and inorganic real co-assembly happens in solution. That was the idea, and we looked around for materials, and fortunately one of our colleague, Professor Murthy from our own institute, working on a beautiful material which is called amino clay. These are aluminosilicate materials which is functionalized with propylamine groups. The beauty of this material is, although this forms nice layered compounds in the solid state, as soon as it put it into water, they exfoliate, they get protonated, and because of the repulsions between this cationic group, they exfoliate and nicely solubilize in water. Okay? So we thought this is a nice material. Can we do an ionic self-assembly in solution? So we came up with a variety of anionic dyes, so that a co-assembly of this molecule should result in a cross-link network and a luminescent material, hybrid material we should be able to make. So this was again a simple concept we tried, and you can see that. So one advantage is that the intercharge distance in this anionic, clay material is much shorter compared to the intercharge distance in the chromophore. So what happens once you mix it, instead of lying parallel onto the surface of this clay molecule, they act as sort of cross-linker, and we get a cross-link material, and we get supramolecular assemblies of these hybrid materials. Okay, and you can see that this is a coronic salt, which is blue MC. This is blue MC material. You can see that it forms a nice blue hydrogels, and you can also transfer onto a film, and still it retains the blue fluorescence of these molecules. So there is the aggregation is minimized in such materials. And similarly, this is a perylene, which is very high quantum yield. This perylene tetracarboxyl is close to 1 quantum yield material, and you can also make a device of, film of this green emissive materials on surface. And another advantage of this silica material is they are highly transparent, so that is another added advantage, and synthetically very simple. But one beauty of this approach is, unlike all other hybrids, we can get different states of molecular organization and luminescence by just controlling the ratio of dye to clay, okay? Which is not possible in MOF, or it is not possible in PMO. What I mean is, you can just vary the ratio of the clay materials to the dye molecules, okay? So what happens is, if you take lower amount of the clay material, you can induce the aggregation of the chromophores. So you get a different emission out of it. But as soon as you increase the concentration of the clay molecules, the number of chromophores on the clay molecules will be reduced, and you reach a kind of exfoliated state where chromophores are attached to the clay molecule. So we can, these are extreme cases I presented here, but you can in principle get any ratio. We can always change the ratio, and you get any state in between. And you can transfer them onto surfaces and retain the molecular organization. So that is one beauty of it. And not only controlling the fluorescence, I will show one example. This kind of molecular organization, changing molecular organization, is also helping us to control certain photochemical reactions, where the topology of these molecules are very important. I will come to that soon. So this is another molecule which is recently came up, which is called tetraphenyletherine, which is called as a AAE molecule. This has come up with Tang. Tang has introduced this molecule. So as I mentioned in the previous slides, that once some molecule, this particular molecule is non-fluorescent in solution when they exist in free state because of the rotation around this double bond. But as soon as it goes to an aggregated state, or if we can restrict the rotation of this molecule, it is highly fluorescent. So that is why it is called as a AAE molecule, aggregation missing molecule. Okay, you can see that this is a state where we just restrict the rotation. There is no intermolecular interaction. There the fluorescence is high, and when it starts aggregating, indeed the fluorescence is quenching, which is although still higher than the in solution. And also we can, as we go to higher ratios of the clay materials, we can get exfoliated state. But this is not what I'm going to talk about. What we found is, so this is the change of fluorescence intensity with the ratio of the clay material. What was more impressive was, so there are certain, this molecule has a double bond, so it can undergo several topological photoreactions, okay? So what we found that in this particular state, when state A, when the molecules are very close to each other, this molecule was supposed to present as a most photostable molecule, but it came as a real surprise to us. We found that when these molecules are very close to each other in the state A, when they are aggregated, you see that there is a nice 2+2 cycloaddition. But as soon as we change the ratio of the clay molecules to the other state, you shine light, you get a Kreising derivative. Okay, so you can say that just by changing the ratio, we can control the molecular organization, luminescence, and the photochemical product of it. So this, and even if you go to the completely exfoliated state, instead of getting Kreising, we are getting only phenanthrene derivatives. So we are able to control the photochemical properties of this molecule by just using a hybrid approach. Okay, another property is just again by this hybrid approach, we can control the excited state properties. For example, Excimer is an excited state dimer. So these are certain molecules whose excimers are not known, like OPV, Kreising. These are the derivatives. Excimers are not reported. But as soon as they go to these interlaid clay galleries, they arrange in such a way that they form Excimer emission. So this is again can be controlled by just changing the ratio of the dye molecules to the inorganic materials. Okay, so this is working fine. And also, what about light harvesting? So we can incorporate multiple dye molecules into these clay galleries, and you see that as soon as you put a donor and acceptor, you see an efficient energy transfer from the donor to acceptor. With just 1% of the acceptor is required, and you get an efficient energy transfer. And you can again vary the colors, and you can also introduce an acceptor which is yellow emissive here, and you can get a bright white light emission out of it. And the beauty of the system is this is solution processable hybrid, so you can even on large areas we can simply coat it. For example, this is a transparent sheet coated with this light emitting materials. So this method really works. Okay, and how much time I have? Yeah, I'm just finishing. So that is amino clay, and we also have another material which is laponite. Laponite is nothing but a clay nanodisc, which is just 25 nanometer. They are highly monodisperse, so they are 25 nanometer in diameter, and the thickness is around 0.9 nanometer. So the unit cell is the thickness of this laponite. And the advantage of this material is it has two ionic phases, in the sense its surface is negatively charged and its disk rim is positively charged. So if you don't use anything, as soon as you put it into this itself, it forms a kind of assembly. But as soon as you protect this positive charge with a negatively charged polymer like polyacrylate, we can exfoliate them and they are freely soluble in water. Okay, so we have two surfaces and we can make them exfoliated in solution. So now can we use this as a template to organize the chromophores? That was another question we asked. So we have come up with a series of cationic dyes like beryllium bisamides and naphthalene dimers, and you can see that they form once you protect this rim with the polymer, they form nicely alternative arrangements of dye and laponite. So this is, and also these polymers, these molecules forms nice J aggregates and highly luminescent films we can make. Some of them are really self-standing shells. And so you can see that higher order organization from TM and XRD, you see that low angle peak coming up. And so this is indeed an alternative arrangement of dye laponite system. So this is quite exciting to us. And what we are trying further is, since it has two phases, in fact, we can do an orthogonal functionalization of the ionic dyes on the surfaces as well as on the rims. So we can get again multicolor emission either by energy transfer or by co-excitation. So you can get a series of white light or whatever emission out of it. So with that, I would like to stop. So I hope I have shown you that a couple of our approaches to control the optical properties and electronic properties of biconjugated systems through self-assembly. And this soft hybrid approach, we believe that it has a lot of potential because it gives us a lot of flexibility to play around with the organization and photochemical reactions. And thank you all for your attention.
Good afternoon to one and all. First, I would like to thank Professor Pal and Professor Mahan Kumar and other organizers of this conference to give me this opportunity. I'll be talking on sustainable wastewater management in India, challenges and way forward. You are listening to lectures having much high scientific content and all, but I will be talking mostly in general, what is the major problems of today and what are the challenges. So, when we talk about wastewater treatment, this is one of the most neglected services among all urban services. And many cities with a population of more than 10 lakhs have some sort of collection systems. Coastal cities and cities located on banks of rivers discharge the untreated or partially treated wastewater into the nearby water bodies. And I need not tell, you are seeing this one on day-to-day basis. And many places, wastewater treatment is limited to septic tank. And I'll come back to the problem of this septic tank a little later. And uncontrolled and unsupervised use of septic tanks has led to severe groundwater contamination even in advanced states like Kerala. And the Water Pollution and Prevention Act 1974 was the first act to focus on industrial wastewater treatment, and this act was meant to improve the water quality of rivers, lakes and marine water bodies. And this is a common site, and you all know which are the places. This is Delhi, and this is Agra near Taj Mahal, and this is Allahabad near Sangam, and this is Kuvam River, some part in Chennai. So, and anywhere you go, this is a common site in India. And who are responsible? We all are responsible for that one. And if you see the current status of wastewater treatment in India, you can see that we are falling much behind, because not even 20% of the wastewater generated in India is getting treated. So remaining 80% of the wastewater is getting into surface waters and groundwaters, and you know how much of pollution it is causing. And finally it is coming back to us in different forms. And all of us know that most of the diseases, 80% of the diseases are caused by contaminated water. So if you can focus on water quality and sanitation, so you can reduce the bill on medical expenses. And again, this shows the wastewater generation and treatment in India in class 1 and class 2 cities. Class 1 cities generate around 64.26%, and in that one only 26.49% is getting treated. And class 2 cities generate around 8.91, and only 0.34 is getting treated. And are we paying a price for this one? Around 73 million working days are lost due to waterborne diseases. That means around $600 million per year. This was the report in 2011, and 6.4% of Indian GDP is lost due to improper sanitation. And economic loss in tourism industry in India is around 448 million per year. Definitely nobody wanted to go for sightseeing in this type of a river. Everybody preferred to go for rivers like this. And if you see the industries, again the problems are there. There are high organic load coming from many industries like distilleries, high dissolved solids concentrations and other pollutants from pharmaceuticals, pesticide industries, dyes, etc. And small-scale industries have inadequate resources and skills to treat their wastewater, and wherever common effluent treatment plants are put up, it is not functioning properly. And what is the present sanitation model? Okay. This is the sanitation model we follow. So we have agriculture, we are using all chemical fertilizers, and food is coming, it is being used by the people, all the waste is generated. Some part is getting treated and most is going untreated, and this partially treated wastewater, everything is finding its way to the surface or groundwater sources, okay, and sludge also is not managed properly. So all these things are leading to pollution of our water resources. So it requires expensive, and whatever the wastewater management models we are practicing today requires expensive piped infrastructure and treatment facilities, and it encourages water consumption because we have to take the waste for a long distance, so pipes need to have the minimum velocity and all the things, so we have to have lot of water, and does not reduce nutrient pollution because none of our wastewater treatment plant, whatever is presently existing in India, big plants, doesn't have the nutrient removal capacity and pollutes the earth and water bodies with the concept solution to pollution is dilution, and we all know that that is not the solution. So definitely it is unsustainable. And coming to the septic tank, all of us are familiar with, but this type of site is also very common in India because the septage from the septic tank, whenever the septic tank is overflowing, you call the people to clean the septic tank, they'll collect it in tankers and nobody bothers where they are going and discharging it. Wherever you have, they find some place where people are not watching, they go and discharge it, and it is having millions and millions of pathogens and high organic load, so that will be contaminating. And septic tank, you know that it will be acting as only as a settling tank and little bit of digestion. The water coming out of the septic tank will be having very high pathogen concentration and organic matter. So we should have a proper soil treatment system. So this is the basic concept of any septic tank design. But people conveniently forget about this part. Only this tank will be there, and whatever the effluent coming, it can directly percolate into the water or into the soil, and most of the places the groundwater table is high, so naturally the groundwater is getting contaminated. And what are the problems of improper wastewater management? I need not tell, most of the rivers in India are contaminated. So you are reading in the paper, Ganga river, Yamuna, Adayar, Kuam, any city you take, the water is highly contaminated. And contamination of groundwater sources, if you see Kerala, you can see that around 250 septic tanks and 230 open wells in 1 square kilometer of area. So as a result, what is happening? They don't have proper soil treatment. So 85% of the open wells are contaminated by fecal coliforms. So that is the status there. So in the recent past, there is a paradigm shift. Earlier we were considering wastewater as a problem. Now at least people started considering it as a resource. So you can see, or you must have heard about new water scheme in Singapore, because they are recycling all the wastewater generated in that country, and treated domestic water is used for industrial purpose. Chennai, some of the industries are using the treated wastewater, and zero discharge norm is essential in major industries, and recycled wastewater for domestic use like toilet flushing and all are picking up nowadays. So when we come to wastewater management system, what is the best thing to do? Okay, so that's the question. But we can have different types of wastewater management system. Either we can go for conventional centralized system. What does it mean? We are generating the waste in a city, collecting all those things through that big sewer pipes and taking it to the extreme end of the city and treating it and discharging it. That is known as centralized wastewater treatment system. And centralized systems are usually planned, designed and operated by government agencies which collect and treat large volumes of wastewater for the entire community. They make use of large sewer networks, major excavations and manholes. And in case of centralized systems, the treated wastewater is reused, disposed of in places far from the generation point. So public interaction is much less in such cases. In decentralized systems, okay, treat wastewater of individual houses, apartment blocks or small communities. So these systems treat and reuse or dispose treated wastewater at or near the generation point. So this is an example of centralized system. So this is the Trichy city. So you can see that the part of the city which is lying the other side of the river also, everything is collected through this one and bringing here and getting it treated, okay, through some oxidation ponds and all. So if you talk about recycle and reuse, it will be very, very costly in such systems. And the example of decentralized wastewater treatment is this. You have some housing colony, individual residential houses and educational institute, or a small community, you have a wastewater treatment plant there, okay, and it is very close vicinity of these houses and all. So the treated wastewater can be reused in this community for various purposes like toilet flushing, gardening, agriculture, etc. So this will be having, if you look into the sustainability, this may be more sustainable compared to centralized system. And if you see the government policies or present scenario, wherever wastewater is collected, mostly treatment plants are not there, because government wanted to distribute the money to all the places. So somebody will get money for the wastewater treatment plant, somebody will get the money for laying the pipeline. So this is one of the major problems, and places where treatment plants exist, enough wastewater is not collected. Now we are evaluating all the wastewater treatment plants across India. We could see that not a single wastewater treatment plant is operating for the design capacity, because the underground sewerage system is not existing in many places, because they have projected the population for 30 years and designed the plant, but this is the problem. The plant is not able to get the wastewater, and wholesome approach is missing. City sanitation plant, government made it mandatory, but many cities are not coming up with this one. Under JNCASR, funds are provided only for asset creation, so nobody is bothered about operation and maintenance. And if you talk to the people, these are the problems. No funds are available for operation and maintenance. Power supply is erratic, lack of skilled personnel, wastewater treatment gets least priority and fund allotment, and proper billing system is not existing. And the biggest problem is, though willingness to pay is there, willingness to collect the money is lacking in the government. And this I have taken from Pollution Control Board website, who are supposed to be the enforcing agency. They are telling that the major factors responsible for water quality degradation is untreated wastewater. You can see that one, read, okay, when you heard. So they are telling that the major problem is because of this untreated wastewater disposed, okay, and municipalities, you cannot put the mayor or the government officials in jail, okay, for not treating the wastewater, whereas they can do the same thing for the industries. And that is about the major wastewater. But now when we talk about recent issues in water quality, okay, you must have heard about this endocrine disrupting agents or pharmaceutically active compounds, etc. Because we all use different types of medicines, and in India, we don't have any restriction to buy any type of medicine across the counter. So all of us consume much more medicine than needed for even small illness. So, and when we consume these medicines, only very little amount is absorbed in our body. Around 40 to 60% will be excreted through urine and feces. And if the wastewater is not treated properly, what will happen? All these compounds will be coming into the water bodies, and when we use the water, the conventional treatments will not be removing them, so we will be unnecessarily taking these pharmaceutically active compounds into our body, and that is creating lot of problems. So this is a major issue, and it is recognized in the recent past. And the sources of emerging contaminants, okay, it can be metals and plastics, paints, cosmetics, pharmaceuticals, antimicrobes, soaps, shampoos, perfumes, flame retardants, and any chemical, any new chemical you, okay, talk about, all those things are coming under this emerging contaminants. So now I'll come to the research by our group. Okay, so we are looking into some aspects of these things. So we have many ongoing projects on various aspects of this wastewater management. So this is something now we are looking into: high voltage pulse stream corona discharge for water or wastewater treatment. Okay, so this is truly interdisciplinary work, okay, with electrical engineering department, because pulse corona and all those things. So what is happening here? Okay, as I told, okay, this is the report by CSC in 2003. Many of the bottled water, you must be remembering this report, many of the bottled water are reported with many pesticides in that one. So you know that all these water bodies are contaminated with these micropollutants. So what is this technology? High voltage pulse streamer corona discharge is something like your football play or a reservoir. We are storing high energy and releasing at once. So that high energy is available for the destruction of these pollutants. So you can see this one, okay, so high voltage is there, so a corona plasma is generated here. As a result, you will be getting highly, okay, oxidative species like hydroxyl radical, nascent oxygen, HO2, H2O2, ozone, etc. And along with that one, you will be having UV radiation, high electric field and intense waves. And this is coming under advanced oxidation, and you can see the oxidation potential of all these species. So it's a chemical process induced in water. So these are the chemistry behind it. You can see that formation of ozone and its dissolution in water, then formation of hydroxyl radical from ozone dissolved in water, and formation of hydroxyl radical via electron impact dissociation of H2O, and formation of hydroxyl radical via reaction of excited oxygen atom. Okay, many reactions are going on here, and we can generate this reactive oxygen species through different approaches, either discharge in gas stream, discharge in water, or a combination of this one, hybrid systems. Okay, that means discharge in water as well as the gas phase, so that you will be getting a better system. My circuit diagram is not coming here. So this is what we have done in the lab. This is our experimental setup. Okay, so this is the electrodes. Okay, so when we pass the high voltage, you can see that the corona or plasma is generated here, and you see, okay, this is methylene blue dye. Okay, we could decolorize 50 milligram of this methylene blue in this reactor within 2 minutes. Okay, so within 1 minute the color is like this, and within, okay, so this is about the color. And okay, so these are the reactive species coming into the system, and we have quantified all the reactive species with respect to time, how it is generated in the system and all. So these are the quantification we have done. So this is hydroxyl radicals and hydrogen peroxide. After some time the hydrogen peroxide is getting dissociated, then ozone and superoxide radicals. Okay, so this is generating all these high power oxidative species. And we have looked into the kinetics also, and energy efficiency evaluation of ROS we have done, and okay, how this hydrogen peroxide is varying in different environmental conditions we have looked into. So now we are using this system for disinfection as well as the pollution removal of other pollutants. You can see that a bacterial concentration of around 10 raised to 7 log, not 10 raised to 7 numbers could get reduced within 4 hours when a voltage of 23 kilowatt is applied. As the voltage reduces, the time is increasing. Okay, and here what we have done, instead of giving the continuous pulse, we have given 5 minutes and 2 minutes break like that, and we could get the almost similar results. Okay, and we have also studied, because in the nature we will be encountering other species like alkalinity, then pH will be varying, turbidity will be there, humic substances and other organic substances will be there. So we have looked into the effect of all these components in water, how it is affecting the efficiency of the system. And we also did the optimization under different conditions, and we have developed some empirical model for this one. Okay, and this is the model prediction and our experimental results. Okay, and this is our dye degradation. I told you 50 milligram we could degrade in 2 minutes time, okay, with using this technology, and total TOC reduction was around 60 to 70% during that, within that 2 minutes. Okay, and color difference. Okay, so, and we also looked into the complex compounds like pesticides, etc., how it is getting degraded. You can see that around 1 milligram of carbofuran was degraded in within 3 minutes time. Okay, and okay, this is a pharmaceutically active compound. Okay, so we could see that this technology is applicable for the removal of. Okay, so this type of new technologies will be a solution for almost all the pollutants. Okay, and another thing we are looking is photocatalysis under visible light, because you know that photocatalysis is a very well known technology and people are used it for many years. So what we are looking is how can we develop this photocatalysis which will work under visible light, so that if you want to apply this one for rural areas and all, okay, this may be okay useful. So there are various methods which which can make this photocatalyst work under visible light. One is photosensitization or dye sensitization, or we can go for nanocomposites. Okay, so we are trying with Fe2O3 TiO2 composites. Okay, and another one is doping. So we tried earlier with N-dop TiO2 and we were getting very good results. So now we are trying with carbon dop TiO2, because carbon is having many other properties compared to nitrogen. So it may be a better solution for water treatment. So this is the characterization of C-dop TiO2. So this catalyst also, we have done the complete characterization of that one and optimization of the system parameters, etc. Because different technology we follow the same experimental procedure. Yeah. So we have looked into the different mixed pollutants and all the things, And another thing we are looking into is development of wastewater treatment systems for industrial and domestic wastewaters, how various reactor configurations can help in the pollutant removal and all the things. Okay, here what we were looking is, okay, we are using membrane bioreactors and all for various purposes. So how attached dose systems and suspended dose systems will be performing, especially when you use these reactors for pharmaceutical wastewater or any other industrial wastewater which contains large quantity of VOCs, and we could see that the attached dose system performs much better compared to suspended dose system, which is most conventionally used. Okay, here the VOC escape is very little compared to this system. Here around 120 is happening. Here we are getting only 0.6 milligram of VOC coming out of the system and all. Okay, so I think I'll go to my last slide. So what is the way forward? An integrated approach is needed, combination of centralized, decentralized and on-site treatment systems, and recycling and reuse is very essential. Combination of technologies according to the requirement. We cannot tell that this technology is always better, so we have to go for a combination of technologies, and whenever needed we have to go for tertiary treatment. The secondary treatment alone may not be suitable, and definitely there should be a policy change to make the system sustainable, and proper enforcement. This is lacking in India because no enforcement as such. Then capacity building, because if you go to any treatment plants, the people whoever is operating the system doesn't even know what is happening in the system. So thank you very much.
My question is, how much efficient this process is in terms of economy? Because you need a huge amount of electricity for one corner research, right? So have you tried it for?
What we are doing is we are measuring, we are conducting the GCMS analysis. Okay.
We have, suppose if you know the end product.
Yeah, so we have.
Then that will answer the
Yeah, so we have looked into the complete pathway, and okay, we have tried organic substances are there. We are taking the mass balance of that one and seeing that one whether it is coming into the solution or not.
So, thank you.
Yeah, thank you very much.
I'll be talking about climate change and its impact on water resource of a river basin. Here I try to focus on these issues. First of all, we'll briefly talk about what are the climate change scenarios, and we try to talk about what is the need for going for downscaling to do some hydrologic investigations, and then we talk about what are the different approaches that we can use to downscale hydrometeorological variables for a river basin. Once we obtain the climate information for hydrology, to complete the hydrologic information as extraction, we also require remote sensing, GIS, and DEM, and we try to see their role and how we can try to utilize them. And finally, using all of them into a reasonably good conceptual hydrologic model, we try to look at what's going to be the future in terms of river flows in a basin into the future for a given climate change scenario. So that's what I try to focus on. Climate change is happening. Only question is to what extent it is happening at different locations may be debatable, and that I'm not going to focus on. But assuming that it is going to happen, what all we should do as far as our preparedness in terms of sustainable water management is concerned is what I would be focusing on. And there are many driving forces, and these driving forces, depending on the quantum of each of those driving forces, we do have different scenarios that are built in, and for each scenario we have to look at what's going to happen for our water resources in a given basin. So these climate change scenarios basically refer to a plausible future climate that has been constructed to explicitly explain the potential consequences of anthropogenic climate change and also to some extent natural climate variability. So these storylines were prepared or suggested by Intergovernmental Panel on Climate Change, which is referred to as IPCC. And IPCC basically tried to construct storylines based on their expectation of how the world is going to develop into the next century. So one possibility is, each one of them are referred to as different storylines. If you look at A1 storyline, it refers to future world of very rapid economic growth, global population that peaks in mid-century and then declines thereafter, and rapid introduction of new and more efficient technologies. Then A2 storyline talks about very heterogeneous world, continuously increasing global population even after mid-century, and economic development is primarily regionally oriented. And when you talk about B1 storyline, convergent world, more or less same population growth as in A1, but rapid changes in economic structure towards service and information economy, which should try to balance to some extent. And then B2 storyline, again, emphasis on local solutions to economic and social and environmental sustainability. So based on these major storylines, we try to talk about different possibilities. So there are 6 scenarios developed. One, these 3 are A2, B1, B2, based on that. And A1 is one expected to be most plausible. So for A1, they again looked into 3 possibilities, that A1, more fossil fuel intensive, A1 with the balance between fossil fuel and non-fossil fuel like other technologies, solar power, etc. And A1T, predominantly non-fossil fuel. So if we try to do that, then how the world is going to develop and how the emissions are going to change is what we are trying to look at in terms of climate change. So typically what we do is we try to use 1990 range as a benchmark, and based on that, how the future is going to be for each of these scenarios that I have mentioned to you is what is projected here. And based on that, we try to have this kind of borderlines or boundaries, 1 to 3.5 degrees Celsius rise by about 2100, or CO2 doubling, whichever is likely to happen. And that's as the boundary line or extreme end of the 2100, we try to look at how the climate is going to develop to that stage. Now, to do that, to develop this kind of climate scenarios, we do look at a large number of climate variables like maximum and minimum temperature, precipitation, radiation, cloud cover, specific or relative humidity, vapor pressure, wind speed, and so on. Each one of them has a serious impact on climate, and specifically if you want on precipitation. So we try to look at these aspects and try to look at them at different vertical levels into the atmosphere and see how the atmosphere is likely to respond for a given rate of growth in terms of emissions. Now, one of the most popular approach for that is using GCMs, which are referred to as general circulation models, which basically talk about circulation over the entire globe. And based on that, we try to look at what's going to happen in a globe at a very coarse resolution. So something like this, we have a certain number of vertical grids into the atmosphere. At every grid level, we look at each of those climate variables like humidity, temperature, and so on and so forth. So many number of vertical levels into the atmosphere. And then we also look at so many levels into the oceans. And that is for one grid. Like that, we should do it for the entire globe. If you even call it as 1 degree by 1 degree, we are talking about 360 degrees by 360 degrees number of grid points. So that's very good, and every place at every grid we try to look at the mass balance of all these things, like conservation of momentum, conservation of mass, conservation of energy, ideal gas law. All these things will be made sure that we try to adhere to all of them. But then that's as far as global climate is concerned. Once you try to look at that global climate at that spatial resolution, which is not really good enough from hydrology point of view, what happens here is even if you consider it as a 2 degree by 2 degree as one grid point, which is pretty good for a global climate, that itself covers a huge amount of area in terms of river basin. It is so large that the topography which may look like this on a natural terrain will be represented or approximated in this fashion in a GCM, which is a gross approximation. And typically a GCM grid point will cover about 300 kilometers by 300 kilometers as one unit, or one pixel if you want to refer to image processing technology. Now, but what we require for hydrology is at a 50 kilometer resolution, or for urban hydrology at 10 kilometers or even finer resolution. So we have GCMs which are working at a very coarse spatial resolution, and we have impact models which require the information at a very fine spatial resolution. So what we do is we try to bridge this gap, this large gap, using what is known as downscaling. And to do the downscaling, we try to do by dynamical downscaling or statistical downscaling. And dynamical downscaling means basically what we try to do is we try to put that grid point information as a boundary, and within that we try to do it a very small or very fine spatial resolution. And to do that, we have to run again a GCM, which is referred to now as RCM, or Regional Climate Model, and try to do it. Unfortunately, for our country, as of now, there is no RCM existing. So the only option that is available then is to talk about statistical downscaling. So what we try to do here is we have this climate information available at a grid points like this from a GCM, and the information that we require is at such a small location like this. So we try to use this information to extract the information at this location. So we try to develop some kind of functional relation between what is happening at this location to what is happening at all these grid points, surrounding grid points, and based on that we try to extract the climate information. Now, to do that, there are so many approaches that we can use. The one that we have used here is referred to as support vector machine, which is a very popular nonlinear approach to develop the relation between a causative variable and the one that we are interested in. So I will not go into details of it, but just let me just say by one line that if you have two features which can be separated by a nonlinear curve like this, in support vector machine what we do is we take it into higher and higher dimensions, and finally at one dimension that separation will be a linear with a line instead of having a curve. So that we try to achieve by using support vector machine. And there are so many approaches that we can try to do, but basically the word support vector comes because of that line, the points which are very close to it are referred to as the vectors which are actually supporting that linear segregation. And that's why they are referred to as support vector machine tool. So basically that tries to develop a functional relation between large scale climate to a hydrologic scale climate information. So here, I'm sorry for the quality of this slide. Here I just try to show a kind of flow chart where I try to mention that if you have the climate information at a global scale or at a grid point scale of a GCM, then we try to use all the information. I mentioned to you there are so many vertical levels into the atmosphere and also into the ocean. So all the information that is available at a one grid point among all these variables, we decide which are the variables which are actually controlling the precipitation, for example, and try to identify those variables. That is, we are referred to as probable predictors. So identify those probable predictors, and among those probable predictors, then we try to develop the support vector machine. But again, there is a small statistical problem there. In terms of these probable predictors, themselves may be correlated with each other. And if that is the case, then we will be unnecessarily talking about considerable amount of statistical redundancy. To overcome that, we go for what is known as principal component analysis. And based on that, we try to extract the principal components and use them as the probable predictors. And to train the SVM, as a matter of fact, we have to also use the genetic algorithms for training the network. So once that is ready, then what we are doing is, if you give me the climate information at a coarse spatial resolution from a GCM output, I try to obtain the information at a fine spatial resolution for a river basin. That's the basic idea of this support vector machine downscaling approach. Now I try to demonstrate this for a case study. This is Malaprabha River Basin, which is part of Krishna River Basin in Karnataka. And you can see that the river basin looks this small when compared to the GCM grid points that are available on this same map. Okay? So you can see that this looks like a very small area, but this area itself is about 2,564 square kilometers, pretty large area. So that's the area for which we want to obtain the climate information based on the GCM output that is available at all these locations. Okay? So we try to do that, and while we are trying to do that using GCM output, we try to get that information for each of these causative variables for runoff, like precipitation, maximum temperature, minimum temperature, wind speed, relative humidity, and solar radiation. So each of these variables are downscaled at a daily time scale to the river basin based on the GCM output that is available. I will not go into details of it, but just show you the summary to give you what are the possible probable predictors. For example, if you want to talk about precipitation, okay, you are talking about 75,000 square kilometers is the one that is represented by grid point, and you are talking about river basin which is of 2,500 square kilometers. Okay, and we identified what are the probable predictors based on the correlation analysis, and these are the predictors. temperature at different vertical levels, geopotential height, specific humidity, zonal and meridional wind at different vertical grids, and so on and so forth. So these are the possible causative variables, and all of them on which we apply principal component analysis and identify them at the relation between them and the precipitation that is available for the river basin. So based on that, we develop the functional relationships. So we get the rainfall. In the same way, we try to obtain maximum and minimum temperature. Please note the causative variables are completely different. Then we obtain the wind speed, we obtain the relative humidity, we obtain the cloud cover, and stream flow. This is one thing that I will be focusing more, because my interest is basically to talk about river basin flows. So I try to show the results. What we did is we tried to do this downscaling. GCM output is available on a dial time scale for the next 100 years. So we are talking about 100 years into 365 number of days for which data is available. Okay? And that data is now downscaled to the river basin at a finer spatial resolution. So I don't try to show all the data in 365 into 100 years, but I just try to show it in terms of box plots like this. Let me show you one example here. You can see here, this is observed pattern of the past. This actually helps us to develop the SVM. So that, if it is comparing well with what we are actually downscaling with the help of GCM, if these two are reasonably comparable, then we are talking about they being doing well. That means the upward vector machine tool that we have developed is doing well. That is basically to ascertain that that SVM tool that we have developed is doing well. This is based on the past data that is already observed. Now, once that is done, if you recall, I have mentioned to you different climate change scenarios like A1, B, A2, B1, etc. Okay? So for each of those scenarios, for the next 100 years, we obtained the downscaled climate data at this river basin. And that is shown here on a 20-year time scale. 2001 to 2020 is just one box, and 21 to 40 is another box, and so on and so forth. And this is for relative humidity. Like this, we downscale the information for each of the climate variables, like this is for rainfall. Okay. Now, interesting aspect as far as rainfall is concerned, if you look at most of the climate change scenarios, into the future, the rainfall is projected to increase substantially, which is reasonably good news as far as that basin is concerned. Now, this is for maximum temperature. Of course, it is projected to increase. For minimum temperature, the increase is not that high as that for maximum temperature. And this is for wind speed. There's hardly any difference because most of it is on the leeward side of the Western Ghats, so the effect is very less. And cloud cover information. Now, that forms a major input as far as any hydrologic model is concerned to estimate the stream flow in a river basin. But that's as far as climate variables are concerned. In addition, we also require what is the land use, land cover change, what is the drainage pattern, and other information to give it to a conceptual hydrologic model to model it. So there are so many hydrologic models which are available to consider the climate information, land use, land cover information, and so on and so forth to get us the stream flow at a given basin. I will be talking about one such model which is referred to as SWAT, Soil and Water Assessment Tool, which is considered to be a pretty good model over different continents. It is applied and it is considered to be reasonably stable. Of course, the one major plus point is that the source code for it is freely available. Okay. So this model is implemented on a GIS platform, ArcInfo GIS platform, then it is called as ArcView SWAT. And this model can consider the climate information, which is essential. In addition to that, we can talk about the drainage pattern, we can talk about the land use, land cover change, which are also equally important to talk about the amount of runoff that we are going to get for a given rainfall pattern on a river basin. So for that, we require the land use, land cover, and this land use, land cover information for the Malaprabha catchment that I have shown you is obtained using satellite remote sensing, and the information that is shown here is from Indian remote sensing satellite. Both LIS-3 as well as panchromatic data were used here. And using that, we try to obtain different land use, land cover categories like agricultural land, built up land, forest land, and so on and so forth. And this is the soil cover map. This is again obtained from remote sensing, but it was also corroborated with soil maps that are available from Nagpur. Then this is actually the digital elevation data, which is obtained again from another space technology, which is referred to as the shuttle radar topography mission, which basically gives us the elevation information at every 80 meter by 80 meter grid points for the entire country of our region. Of course, it is available for the entire globe. For our region, it is approximately 80 meter spatial resolution. So this digital elevation data clearly shows you that this is the valley portion, and this is the valley portion, and this is the ridge line, the boundary of the basin. Okay? So within that, we try to use the elevation information, and based on that, we try to derive what is known as drainage pattern. So the drainage pattern is basically derived based on the elevation data that is available. And this shows the drainage pattern. So we can see that this entire drain is draining into this location, and from here it is joining this. It's like almost like you have so many tributaries of a river. Okay? So finally, it all gets collected at this location. So what we have is the stream flow that is measured at this location. We have the rainfall occurring over this entire basin. So we try to calibrate the hydrologic model that I have showed you, and based on that, we try to estimate or try to parameterize this model configuration in such a way that the runoff that we are obtaining here is comparable to what is actually observed. And once that is done, then we say that our SWAC model is now ready for implementation for the future climate scenarios. So these are the collection, as I said, some PowerPoints, and based on that, we try to look at the sub-basin outlets, etc. So we get the drainage information and use that to get the runoff, and all other parameters like land use, land cover information, etc. are provided in terms of different types of land use, land cover, like pasture, water bodies, urban area, and so on and so forth. Once we have this information provided for the entire basin, then we get the runoff, that is the stream flow at the mouth of the basin, and that we compare with what is actually observed and see how well they are comparing. And if they are comparing well for the recent past, we assume that that relation holds good into the future. And based on that, based on all the information that we have downscaled so far in terms of each of the variables like humidity, temperature, etc., will all be provided now into the SWAC model on a daily time scale to obtain the stream flow for the next 100 years. Okay? I can again show you a plot like this. Okay? Of course, this is basically to have the confidence in the past. Then we are talking about for each scenario, how the stream flows are projected into the future. So you can see again clearly, like the way rainfall is projected to increase, the stream flow is also projected to increase. And just at the location where we are measuring the stream flow, there is a dam. So that dam, which is also called as Malaprabha Dam, can store all this water. Therefore, even if there is an increased amount of flow, that flow can be stored in the dam, and that is very, very vital for Dharwad and Hubli districts, where drinking water is supplied from this dam, apart from huge amount of irrigation area. So that brings some amount of stability as far as the future climate for this basin is concerned. I just want to warn that this is not going to happen for every river basin. We have to do this analysis for every river basin. We have been doing it for many river basins. Okay? But as far as this river basin is concerned, climate change seems to be a positive story for this river basin. So this is what I want to say as far as climate change modeling is concerned. Whatever the amount of development takes place, all that will have a vital input in terms of river flow or river basin flow estimation is concerned. If we can do that, then using that kind of stream flow projections into the future, we can talk about how we can utilize that water in a sustainable manner. Okay? And one major challenge is I have projected that stream flow is increasing, but it may be increasing with high intensity. So whether we can store it at that intensity or not is also a crucial issue. Other than that, all these tools should be very useful to talk about climate change impact assessment. Thank you.
You heard him talk from Wastewater Institute for Applied Analysis and Stochastic, Berlin. We had Professor Raja Banerjee from West Bengal University of Technology, Kolkata. We had Dr. Surojit Ghosh, Indian Institute of Chemical Biology, Kolkata, and Dr. Taslim Arif Syed, Director and CEO, Center for Cellular and Molecular Platforms, Bangalore. So these people, some overtly, some covertly, saw your posters and graded them. Among all the judges, Professor Arne Lutzen and Professor Jan Volker said they will choose the best 3. So they did not give ranks. So that's why you see, so all are given same numbers. So how it is, so you see, so the poster numbers are given. So these are the posters they marked for, their liking, so their selection. So 1 means that you get 10 points, 2 means you get 8 points, 3 means you get 6 points, 4 means you get 4 points. Okay. So accordingly, whichever poster have been given marks, I have added them up. So you see 10 for 40, post number 40, 41 had 2 markings, so 10 plus 10, 20, and then likewise post number, if you, can we scroll?
Yeah.
Okay, so likewise we had marked each of them, and we have added up the numbers. So as per this assessment, the first,
mention the people who spoke or not.
yeah, so the people who had the Professor Manju Bansal's student Asmita Gupta. Is she here?
I think it had started backward.
Oh, it's okay. So, congratulations, Asmita, for your. Number 2, how do we go? Number 2 is K. Raja. 2 judges, so he has 10 plus 10. It is interdisciplinary, so he did not figure in any other selections, but he managed number 1 in 2 selections. So, and is Dibbojyoti. He managed 2nd position in 2 posters, with two judges. And we have 14 marks, and they're at the 4th position. One is Abdul Samad, and another is, I think, Soumya Banerjee. So about the poster prizes, and now we will come to the end, almost the end, and this is without support and guidance of many people. First and foremost, of course, Professor Manju Bansal, and then subsequently the thematic leaders. First, Professor Nagesh, Professor Parthasarathy Mukherjee, Professor Shashi Kumar Ganeshan, Professor Vidyanand Nanjundaya, and Professor Mohan Kumar. So these people have helped us get the exciting speakers, which would not have been possible if I were doing this all by myself. So a round of applause for them. Okay. Next, credit for this Kolleg goes to volunteers. Volunteers who have worked hard to get everything going on time. So volunteers, if you can come to the stage and let everybody appreciate what you have done. So Pratiti Bhadra, if you can come. So she has run around and gotten things done, many things. So and next is Prachi Sao. Prachi, are you here? So she coordinated the food arrangements, and also the same case in guest house, she has woken up participants who were sleeping. 3 who had manned the registration desk and given remuneration for all the participants who were traveling, and she is the person from whom you have to get your money, the poster prize. And then we have other students one by one. Akhila, who maintained the time and ran around the speakers. Sanjay, who manned the laptop. Only few groups, but he maintained the speaking time very well. And there are a few other students, Dibojyoti, and then Baban, and Shivaratna. I can't see anybody else. Yeah, Vivek, where is Vivek? Okay, Manasa. Okay, she has not turned up today. Okay. So let us thank all these people who have helped us to organize this conference. I hope you have enjoyed the lectures. The video and the photos will be put on the web. The video will be on the YouTube, and you can share it with your friends. And if you have comments, appreciations, write to Kolleg at Parlab, from which you have got an automated email, and I'd be happy to forward it to the Humboldt Foundation. If you have criticisms also, you should write to us so that we can improve. I thank you for your participation. Thank you so much.